Alright girls, let's have a look. So hopefully what I'm going to do today is just going through the key points of the P7 radioactivity topic. So I know you have your test coming up next week. It's going to be the first lesson we have. So I'll break it down into just the main key points that you need to remember for your test. Okay, so the first thing is, so the radioactivity series, or the topic itself, is split into these points here. So I'll talk about atomic models, which are the structures, and Rutherford model, why it is important. Okay, and we'll look at changes in the nucleus. So what is alpha, beta, and gamma? Look at some decay equations. Okay, uses of alpha, beta, and gamma, half-life, some medical uses. There's some key points that we need to remember, and finally fission, describe it, pros and cons, and finally fusion, pros and cons. Right, let's get started with the atomic models. Okay, so let me just number them. So this one's 1. Okay, let's talk about 1. Okay, number 1. So atomic models. So if I ask you to go to draw the atomic models now, so everyone is going to. Okay, so if I ask you to draw it, so all of you should be able to draw. We have the nucleus in the center. Okay, and around it we have the electrons. Okay, the electrons. Good. And we have the nucleus. So inside the nucleus, we have the proton and the neutron. Okay, so let's say, okay, good. All right. So the whole thing is the atom. So the whole thing is the atom. But the atom consists of electrons that goes around it, and inside, so this part here is the nucleus. Good. And in the nucleus, we have the proton and slash the neutron. Good. Okay. So let's take a look. So if you guys remember, the proton. Okay, the proton, the charge for the proton is positive. Okay, positive, positive. Good. All right. The charge for the neutron is just neutral, so 0. Okay, it's neutral. Electron is just negative. All right. Good. Okay. Now, let's talk in terms of their mass. So how massive they are, the size. So again here, we're talking about what we call the relative mass. Okay, not the true mass, but the relative mass. Because we are comparing them to each other. So if you guys remember, proton has a relative mass of 1, neutron, relative mass of 1. So these ones here tell us that they are roughly the same size. So if I want to draw them, so if I put a column here, let's say draw. So I'm going to draw them. So proton is going to roughly like this, and this one like this. Okay, let's put the P there for proton and an N for neutron. So if you look carefully, they're roughly the same size. So that's why I say 1 and 1. This guy here, on the other hand, electron, they are very, very small. So the size is roughly 1 divided by 2,000. That's how small it is. If I want to draw it, I'm just going to put a dot here. As you can see, they are very small. Good. So this is just, that's what we know on the atom. Good. Let's take a look at the structure. So what you need to know is like roughly how the structure evolved around the years. Okay, so let's take a look. The structure, so I'm going to put the structure here. Okay, so structure. Okay, so roughly you don't need to remember any dates, any big names, etc. All you need to know is, remember, is we started with the solid sphere model. So the Greek thought that every matter, everything around us is made up of little particles. So if you want to take something, so for example, if I take this, for example, and I take a small portion on it, I keep dividing it, so I divide it, I'm left with this one. I keep dividing it until I reach a point where I cannot split it even further. And that is the atom. Okay, so the atom was thought to be unsplittable. So this is the solid sphere. Let me just put it there, solid sphere model. Okay, and then later on, this got developed even further, and then it turns into what we called the plum pudding models. Okay, the plum pudding model says that the whole sphere is positively charged. Okay, however, we have electrons spread throughout it. So these electrons are like the plum. The whole sphere is positive, but these electrons are embedded like plums in it. Thus the name plum pudding. Okay, and we move on. Now, this one is going to be very, very important, because that's what will be the second point here. So that's what Rutherford came along. He did an experiment, and based on the experiment, he redrew this one. So he found out that actually the atom has a nucleus in the center, which is mostly positive, and then the electron goes around it. Okay, and they're very small. Okay, so let's have a look again. Let me just draw this nicely. Okay, that's how we came up with. So this one's the Rutherford. This is very important. Rutherford. And then after Rutherford, people start doing more experiment, and then they have Bohr models. So Bohr models is just what we have the planetary model. So we have the nucleus in the center, and then the electrons are in perfect orbit. So just like planets. Okay, like you can see, planets, electrons, electrons. Here we go. All right. Now, what you need to remember, you don't need to know the whole thing. What you need to know is, like, we start with solid sphere, how it looks like roughly, plum pudding, Rutherford, very important, and the Bohr, which is just planetary. Now, in year 10, we're going to be focusing on this one here, this one, and mostly this one. But this one here, since this is the experimental value. Now, we're going to take a look at number 2. Here we go. Number 2. Why is it important, and how did we came across this part here? So here we go. The last section. I'm going to do number 2 here. Good. So now, Rutherford, he did something remarkable. He took a piece of gold sheet, so let's say thin gold sheet. Okay, gold sheet. Okay, and then he took a particle, which is called an alpha particle. Later on, we'll take a look what this one is exactly. So we take some alpha particles, okay, 1, 2, let's say 3, okay, and then he fired these alpha particles at the gold leaf. He fired it. Now, he saw that it comes in, and then bam, get deflected, okay. So this one tells us that it is hitting the atom, okay, and it is deflected, which makes sense, because objects are made up of atom, okay. And then the second one passes through it, and I was like, wait a minute, if everything's made up of atom, an atom is look like this one, then it just should be reflected, okay. It's just like when you hit a wall, it just bounces back. But how did this one go through? And this one here, again, come in and bounce back. I was like, wait a minute, let me try with more particles. So he had more particles, fired it, passed it through. It was like, wait a minute, there's something wrong. So therefore, this can't be true. So this experiment here, what this experiment is showing that the atom actually looks like here. So this is the nucleus, let's say positive, okay. We have the electron, let's say the electron goes around it, like this, okay. Let's consider one electron from the example. Now, let's redraw this one. We have an alpha particles here. Alpha particles, 1, and for the sake, let's put 2 here as well. Now, let's see. This is the atom, okay. The whole thing is atom, right? The whole thing is the right atom. Now, fire this in, goes through. That's what we're getting here. Goes through. And this one here, when this alpha particle is fired, and then it happened to just be fired at the nucleus, come in, hit it, bounce back. Okay. So what he did is he tried to redraw the model, he said that for the particles to go through it, it means that there must be some empty space, so it can just pass through. And for the particles to bounce back at the large angles, therefore, then there must be something there, and that is a nucleus. Okay. So what I'm going to do now is I'm going to write down these points, these 3 points, for you to remember. All right. Now let's take a look. What can we deduce from this one? So I'm going to write here, Rutherford. So this one's 2. Why is it important? Here we go. So let's take a look. Okay. So we saw that. Okay. So we saw this one. So we saw that most alpha particles, okay, pass through the atom. Okay, all right. Second, okay. What now? They pass through. What this shows, okay, this proves that atoms are mostly empty space. Good. All right. Okay. Third point. Okay. So now what we've done is 2 points is talking about the one that passes through. Now we're going to write down 2 points about the one that is deflected. Okay. So what happened is some alpha particles, okay, get deflected. Okay, they get deflected, but how do they get deflected? They get deflected at large angles. Okay, large angles. All right. Okay, it's just like when something hit the wall very, very hard, it just bounced back. That's what it means by sharp angles. Okay, what does this mean? This means that so this tells us that deflected large angles. Good. This proves that that the atom contains a nucleus. Nucleus. Okay, this is it. Don't worry, girls. This is just a video going through it, and I'll also give you this sheet on show my homework. Okay, so based on this diagram, we came up with pretty much 4 things. 1, the particles pass through it. Okay, and then why is that? This proves that it is most empty space. That's why we just go through it. Second, some of them get deflected at large angles. This shows us that it has a nucleus in the center. Very good. Excellent. Now we can move on to the next part. Okay. Let's bring this one here. Okay, now let's take a look at the changes in an atom, and the nucleus, sorry. Number 3. Put this there. This one's here. Okay. Now let's move on to here. Okay, and we're going to do number 3. Very good. Okay. All right. Where should we start? Let's start with alpha beta. So alpha particles, What are alpha particles? So alpha particles, they will normally use a symbol like this one here. This is the symbol for alpha. And what is it? So an alpha particles, it consists of 2 proton, okay, and so this is n 2 neutron, okay, neutrons. Now if I want to draw this, it's going to look like, let me just put it an arrow, it's going to look like 1 positive proton, so 2, sorry, so there's 2 positive proton and 2 neutron, okay, that's how it looks like. Now which element from your periodic table has 2 proton and 2 neutron? So this is also known as a helium nucleus. Helium nucleus. Now, why we call it a helium nucleus, not atom? Helium nucleus because there's no electron. No electron. No electron. See, only the inside the nucleus. No electron. That is an alpha particles. Good. Let's take a look at beta particles. A beta particles normally do it as B with small tail of it. What is a beta particles? A beta particles, it is a fast moving electron. Okay. Now electrons, okay, let me bring this one here. Electrons are normally found around the nucleus, so in the atom. Okay, it goes around it. It just goes around it. It just stays there. Yeah. However, beta is different because it is moving fast, and then it's just free. Okay. All right. So if I want to draw it, I'm going to draw it like an electron here. So E for electron, and then I'm going to put some speed there. Okay. Doesn't make sense? It's just moving. Okay. All right. And electrons. Good. And the last one is a gamma radiation. Sorry, gamma particles. Gamma particles, they will write it as a Y, but a little thing here, this one here. What is it? It is an EM wave, electromagnetic wave. Okay, it has a high energy. Okay, so if I want to draw it, it's going to look like a wave normally. Sorry. Just like a wave normally. It's very, very powerful. Okay, now the way I've drawn it, you can tell by the size which one is the biggest. So alpha particle is the biggest here, followed by beta particles, and then we have gamma, which is very, very small, just like a wave. Okay, so just by looking at it, we can tell. Now what we're looking at is we looked at something called atomic number and mass number. Let's take a look at this one. Okay, let me put it here. Right. So, from your periodic table, we have an element. Let's take this one for example, helium. Helium. Now, helium has a atomic number of 2 and a mass number of 4. Right? So the number on the top, this is what we have called mass number equal the number of protons plus the number of neutrons. Okay? Right? And the bottom number is called the atomic number, and this one is protons, number of protons only. Okay, good. Okay, number of protons. Okay, note that atomic number equal electron number. Okay, so if we were talking about the atom, so in this case, helium has 2 protons, so therefore it will also have 2 electrons. That's how we can find out about the electrons. Okay, good. Right, and this is a alpha. Okay, so all you need to know is like the top number here is the mass number, it's just the sum of proton plus neutron. So here we go. So it's 2. Okay, if you know 2 proton and 2 neutron. 2 plus 2 go to 4. This one here is just only proton. Excellent. Right. So in the question, they can give you, for example, what can they can give you? They can give you something remarkable. Okay, excellent. But they can give you this one, and then you need to find out the rest. Okay. So example. Okay. Here we go. So let's take an element, for example. Okay. So here we have an element. Okay, could be any element, and one question will tell you. Okay. Proton, neutron, electron. Okay, just give the numbers. Give the numbers. So how are we going to do it? Okay. So let's have a look. This is proton, 90. Good. Neutron. How can we get neutron? So we know that this one here is 228 is the sum of proton plus neutron. So it's going to be like 222 is the neutron, and we don't know, plus proton, which is 90. Okay, so that's what we're looking for. Okay, so therefore, the neutron is going to be 228, take away 90, and we have 238. So neutron, will be 138. Okay, and how many electrons will you have? So like I said, atomic number, which is this one, is the same as proton number, and also be electron number. So here, 90, 90. Good. Now always remember, the mass number, the top number is always the mass number. It's for all the atoms. Mass number, atomic number. Always remember that. Now we'll be looking at the properties of these three. Okay, these are the 3 main particles that are giving out when a nucleus decays. So a nucleus loses part of itself. It will either lose itself by, some of it will be lost either by alpha or beta or sometimes gamma. Also all 3 together. Let's take a look at these 3 properties in the next page. Okay. So the way I'm going to draw it, I'm just going to use the symbols. Okay, so let's take a look. We have properties. Okay, properties. Okay, so we have, what is this? Alpha, beta, gamma. Now let's take a look. So beta is a helium nucleus. So I'm going to, let me just show this table. Okay, it's a helium nucleus. So I'm going to write it as He and 4, 2. Good. All right. So beta particles is it is an electron. Okay. So I'm going to write it as E. Now, what is the mass number? So there's some numbers I need to put there. What is the mass number of an electron? Well, mass number is just an electron, so it doesn't have any, 0. And the bottom one, it doesn't have any proton. It's just an electron. So this one just goes to negative because it is this negative. Okay, and the last one, gamma, is just 0. doesn't have anything. 0 doesn't have anything. Okay. Now, always remember these numbers. Okay. Always remember these numbers. Okay. All right. Now let's take a look. So here I have a thin sheet of paper. All right. Here I have some aluminium sheet. All right. And finally I have some thick dense lead. Can you see? Lead. Right. Let's see which of these three is going to pass through. Right. So let's say I have an atom. Sorry, I have a nucleus. And the nucleus gives off these three, alpha, beta, and gamma. All right. Let's take a look. So imagine that we have a nucleus here. Let's say a nucleus. You got some protons, neutron, whatever. Okay. And this one starts to decay. Now, the reason why you want to decay is so that it can get stable. So the more particles there is in the nucleus, the more unstable it will get. And all nucleus want to be stable. So in order for them to be stable, they need to get rid of some of these particles. Some of them, so to get rid of some of the particles, there are three ways to get rid of it. Either they get rid of the particles by gamma radiation, gamma particles, which is just a wave, just giving energy, or losing an electron, or losing some particles in terms. So these are the three. Okay, now let's take a look. Okay, so this one here, and alpha particles, since it is the heaviest, okay, since if you guys remember, where is it? If you remember the size, since it is the heaviest, then it will be stopped easily by a piece of paper. Even air will stop it. Beta particles on the other hand, since this is a fast-moving electron, and electrons are smaller than alpha, so it will go through paper, but it will stop by aluminium sheet. Now, if the aluminium sheet is very thin, then it can pass through, but some probably like let's say 5 centimeters, 6 centimeters should be enough to stop it. Okay. All right. Gamma, on the other hand, since it's very small and has high energy, you're going to go through paper, through aluminium sheet, and then goes through and stopped by a thick lead. Now, if the lead is very, very thick, then it's going to get stopped. So that's why, if you guys remember, these particles, these sources, they're kept in a lead container, okay, sealed in a lead container, and okay, and then so there's lead underneath, lead on the side, and lead at the top, okay, and the lead is very, very dense, so this will try to stop it. Okay, so let's take a look at, okay, there's also, so this tells you how to, which one stop it and which one go through it, but there are two things that we need to look at. First one is ionization, second is penetration. So penetration is already done for you here, so you know which one it goes through, so penetrate through. Let's take a look at ionization. So ionization means which of these three will lose most of its energy when it reaches a boundary. So let's take a look. Alpha particles reach the paper and stop there. So since it gets stopped, all of its energy will be deposited to the paper. So what's going to happen is we're going to say ionization, power, okay, rank it from, let's say, alpha particles, which is the helium nucleus, Okay. Now the reason why I'm writing like this, in this here, so that you can get used to it. Later on, when we'll be doing the, how do you call it? Decay equation. Okay, good. So this one has a high ionizing power. Comes in, hit, stop, loses all of its energy. This one, medium. Okay, because it goes through this one and then it gets stopped by here. This one has the lowest because it goes through it. Low. Good. Okay, and here if you want to rank it in terms of penetrating power, so we're going to get this one here has a low because it gets stopped easily. This one here, medium again, says medium. This one's high. Good. Now let's take a look at its uses. And if I believe its uses is uses here. Okay, let's do this one first then. Uses, and then we go on decay. Good. Okay, uses. Where do we use alpha particles? Why do we use alpha particles? Interesting. So since alpha particles can easily get stopped by paper, so why can we use them? Actually, so alpha particles in bracket this O get used in smoke detectors. Now, smoke detectors, they're made from plastic, and plastic, it's just like paper, will easily stop alpha particles. That's why it's not dangerous to have alpha particles in your smoke detectors, because your case, because the case, so casing equal to plastic, and plastic stops all the alpha particles from going out of it, so we are safe as long as we don't open the casing. Okay. So how it works, so what happens is inside there's alpha particles. So when there's a smoke, the smoke goes into the detectors and it interferes with the alpha particles. So sort of like stop the alpha particles. Okay, so what happens is, let's say we have inside of our smoke detectors, we got the alpha particles. Normally they just go from one side to the next side. Nothing. The usual. And then we have smoke. Smoke comes in. Let me just take this way. Smoke particles are much bigger. They come in, and then they get in the way of the alpha particles. Now the alpha particles can't reach the other side. Okay, when it can't reach the other side, that's when we get the alarm. Where? Oh well, I don't know. Okay, that's pretty much it. Right. I need another piece of paper. Here we go. Alpha particle. Smoke detectors. The smoke particles pretty much stopped or absorb the alpha particles, and then we get the alarm. Right. But the one that we need to know, which is the simplest one, is the uses of beta particles. Let's take a look. Okay. So beta particles, we use it to monitor thickness of sheet. Okay, so this sheet could be aluminum sheet or could be paper. All right, so let's take a look. So what we have is, the sheet. Okay, we have the rollers here and here. This roller just moves the sheet along. We got the rollers here. Here, good. Now, what we have a so what we have is we have a source. Okay, and this source So in the source there is an alpha source here. So this one will emit, sorry, not alpha, beta particles. Okay, so these are beta. Now, at first, since the sheet of paper, or sometimes aluminium, okay, it's very thin, so so the beta particle can easily pass through. Okay, the beta particle can easily pass through it. And then here we have a detector. Okay, a detector to detect it. Okay, right. Also, if I want to mention here is the detector is called detector is called a Geiger counter. So every time, so what happens, like every time a particle goes through the detector, we hear either a beep, 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 beep. It's like counting it, beep, 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 counting it. Okay, that's the name, Geiger counter. I think that's how you spell it. Good. Now, that's when you have a thin sheet. Now let's say the thickness is start to increase. So thickness starts to increase. Okay, we got the source again. Okay, what's going to happen is we're going to have less beta particle that go through it. So as you can see, here we have plenty. Okay, nothing happens to pass through it, and here we have less pass through it. Okay, all right, and eventually, when you increase the thickness even higher, okay, and then we won't have any. So this one. Okay, eventually none of the beta will reach it. Okay, so this detector is connected to the computer, of course, and then it will start to monitor. Okay, that's how they monitor the thickness, by counting how much beta particles passes through the sheet. And when the sheet is too thick, okay, so there's nothing, then the machine can either stop or do whatever he wants. Okay, this is pretty much it. That's how he uses it. Okay, so this one, since it's pretty straightforward, that's the one that you need to keep in mind. And gamma radiation or particles, we use it to kill bacteria. Okay, bacteria. We also kill it to use tumor. Since very small, we can either use it for this one, or we can use it to sterilize instruments. Okay, pretty much that's this one. Okay, radiation, kill bacteria, kill tumor, kill sterilize instruments. Now, why do we use this one? Because it's very small. Okay, just like a wave, very small, high energy, and it can pass through almost anything. So it goes through bacteria, passes through it and killing it, passes through tumor, killing it. Sterilized instrument is linked to killing bacteria as well. Okay, so if you have an instrument, and let's say my instrument is still new, it is in plastic. So gamma passes through plastic, it's direct, and just like cleans it. Excellent. Right, so well done, girls. Well done. So it's like 40 minutes in, and we're almost halfway there. So this one's done. Let's take a look at the decay equation. Number 5. All right, for the decay equation, since we're dealing with 3 particles, alpha, beta, and gamma, therefore there will be 3 different decay equation, types of decay equation. So there's going to be one for one alpha is giving out, one for one beta is giving out, and one for gamma is giving out. Right, let's take a look. First thing is we look at alpha decay. So you guys still remember this? Alpha decay. Excellent. Now, during the lesson, I've given you some example, and you guys have written it down, which is excellent. You need to know on the equation. So let's take a look. Okay, let's say we have a nucleus. Okay, this is an element, and this element has a mass number of 228, and the proton number is 90. Now, this nucleus here is unstable, and you want to be stable by getting rid of some of its particles that's inside of it, and so for it to be stable, it gives off an alpha. Here we have an alpha. Okay, and then once if it's giving off an alpha particles, this one will turn into a new element, and this new element will be more stable. Let's say we do not know that new element. Let's call it X. Now, how can we find out what this new element is? That's when we need to know the top number here and the bottom number here. Now, what is an alpha particles? So we know it is a helium nucleus. It has 4 and 2. So therefore we can say 4 and 2. Good. Now, what are we missing in the box? What are we missing in the box? Okay. So 4 add what number give us 228? So therefore, this has to be 224. Excellent. Now the bottom one. 2 add what number give me 90? So this has to be 88. Good. So we can say that the new element X is 224 and 88. Now, which element has these two numbers? So therefore, this one. Well, these elements, if you look at these two numbers on the periodic table, you're going to find out that this element X is actually radium. Good. So that's how we know that if this element here decays via alpha particles, this one will turn into radium, which is more stable. So this one here, I'm going to put in bracket, unstable, and then it become stable. Okay, and to become stable, it just give off alpha particles. Now, alpha particles, you can write it as here, like as written here, or you can just put this one here. It doesn't matter. That's how you do it. Good. But always remember 2 for alpha particles, so that you can work out what's missing. Good. Let's take a look at beta decay. Right? What is a beta decay? B, electron is -1, 0. O, E for electron, 0, -1. Always remember these numbers. Always remember these numbers. Now let's check one example. Beta decay. Let's take a look at an element called potassium. Potassium has 40 and 19 proton. Let's assume that this is unstable, and they want to turn itself into stable. And to do so, it needs to get rid of it. It does so by emitting a beta particles, and then we get a new element which we don't know. Let's call it X again. Good. What's the bottom number? -1. What's the top number? 0. Good. Now let's find out what this one here is. Okay. So 0 at what number give me 40? It's just 40. Very good. Okay. So what number -1 give me 19? 20. So therefore, X is 40 and 20. What element is this? We look at the periodic table, we found out that this element is calcium. 40 and 20. Very good. Here we go. Unstable to stable via beta decay. So always remember these two numbers here so that you know you can find this out. And the last one, the easiest one, beta. Oh, I'm hungry. What am I doing? Gamma, yeah, gamma decay. Is the easiest one. Is the easiest one. I can put anyone here. So let's see. Let's say I have uranium 235 and 92. Proton. It decays via gamma and give me a new element which I don't know, which I need to find out. Gamma, if you guys remember, where is it? Where is it? Here we go. Oops. So if you guys remember, where is it? 0, 0. 0, 0. 0 add what number? Give me 235, 235. 0 add what number? Give me 92, 92. So therefore, X 235, 92 is uranium 235, 92. Now what's happening here? Actually, uranium is becoming stable via gamma decay. So gamma decay is just carrying any extra energy that is making itself unstable. Okay, so for example, let's have a look. Okay, so for example, let's say you're sitting down and you had too much energy to drink. So all you do is pretty much you pretty much can't sit properly. So for you to sit down, you need to waste energy. So you just go around running, jumping around. So you're just losing energy, and that's how it's doing. So it's losing its energy, becoming stable. Good. Okay, so what you need to remember is again gamma 0, 0, beta 0 minus 1, alpha 4, 2. These three you need to remember. If you remember these three, then you can solve any decay equation. Okay, good. Decay equation, خلاص, done. Okay, am I missing anything yet? Am I missing anything? All right, yes. Okay, let me talk about isotopes. Isotopes. Okay, girls, if you remember, we did some practice. Well, we did some activities, quiz activities on this one. So isotope